So hi folks, so let's talk about another class of exponential random graph models where we can say something about estimation and some techniques for developing models that are a little easier to estimate than the basic class. And we'll call these SERGMs. And this is going to come out of a paper that I've been working on for a while now with Arun Chandrasekhar. And the idea here is that there's a fairly simple observation that will allow us to save dramatically on computation and also do some nice statistical theorems. And in particular, there are many possible networks, but there's fewer possible statistics. So when you look at how many different networks there are that have on 30 nodes, we get this enormous number. But when we ask how many different triangles could be on a network of 30 nodes, that's a much smaller number. And many networks are going to lead to the same statistics. And so the probabilities actually only depend on the statistics. So in an exponential form, graphs that have the same number of triangles and the same number of links, if the model only depends on triangles and links, if they have identical triangles and links, nature doesn't care exactly how those things are arranged. It just is caring about those statistics. And so what we can do is collapse all these different networks that have the same statistics and just look at the statistics. And that's a much easier space to do computations in, and they'll be feasible, and we can actually do fast and accurate estimation of some of the models that we even looked at before. Okay, so let's have a closer look at this. And so the idea is just based on the idea of sufficient statistics, and in the exponential form that's very easy. So if we're thinking, so now let's let this S of G be the vector of S1 of G, S2, etc. So we've got some K statistics on a graph, and beta is equal to beta 1 through beta k, then we can represent the form as the dot product between beta and the statistics. And the difficulty we were facing before is we were trying to sum overall possible networks. So the probability of a given graph we could write this way. So one way that we're going to simplify this is ask what's the number of networks that have a particular statistical signature. So how many networks have exactly 10 isolates and 65 links? Okay, well, there's different ways you could arrange those isolates. There's different ways you could arrange those links. But that's a combinatoric problem that we can approximate. Sometimes we can find an exact solution. Sometimes we can approximate that fairly easily. So what we're going to do is look at what's the number of networks with a particular statistical signature. Okay. So we can rewrite the probability of a graph. Instead of summing over all possible graphs, we'll just sum over the possible statistics that it could have. So you could have 0 isolates, some number of links, 1 isolate, a bunch of links, 2 isolates, a bunch of links. So you could have different possible combinations of statistics, and then you've got numbers of graphs that could have those statistics. And now what we're doing is, instead of summing over all possible networks, we're just summing over how many different triangles and how many different links a network could have. And that's a very small number compared to the number of atoms in the universe. So now we've got the probability of a graph in a much more manageable form. Okay. Now the second part is that, in fact, we might not want to care about the probability that we saw a particular network. If we think that what is really important is the number of links and the number of triangles, then we can ask, well, we just cared about the probability of a certain observation in terms of the statistic that came out. And so what's the probability of seeing a certain number of links and a certain number of triangles? Well, that's just the number of networks that have that number of links and number of triangles. They all are going to have the same probability, so you can just multiply this probability up. So if this is the probability of seeing one graph with those characteristics, this would be the probability of seeing that number of links, that number of triangles, that realization of statistics. So we've got a statistical form where now what we've done is just collapse things into the relevant properties that we really care about in terms of the network. What's the probability that a network has, that nature generates something that has these particular properties? Now everything is in the statistics space. It's a much smaller space, much more manageable to compute in, and so now we're on our way to doing computation. The difficulty, of course, is going to be in estimating some of these n parameters, but we'll say more about that, and in some cases they're going to be very easy to estimate, in other cases they'll be more difficult. Okay, so at least we've gotten something down to a manageable size. So we're asking, what's the probability of observing a network that has a certain density of link, a certain clustering, certain average path length, et cetera. So you keep track of those statistics, and now we ask what's the probability of seeing networks with those. Okay. Now, one other thing we can do in terms of once we've gone this way, so this came from rewriting an SERGM, an exponential random graph model. We got this representation. But once we're in this kind of family, we could envision a whole set of models. Instead of having the n be the number of particular graphs that have a certain statistic, we could imagine all kinds of different weighting functions that we could put in here. Okay? So you could weight these exponentials in different ways depending on different statistics. So nature might not be counting, it might be choosing statistics in a way that's not weighted by the number of graphs that have that statistic, but it might be weighting them in other ways. So you could imagine that nature weights things in other manners, and we can write down a general class of families. And so these will be the SERGMs, right? So these are statistical exponential random graph models. Everything's done in terms of statistics, and a special case of these is going to be the exponential family, where these k's correspond to the n's, the number of graphs that have a certain observed statistic. Okay, so a special case is going to be the SERGM model that we had before. Okay, so let me just emphasize the idea here. Many networks, many fewer possible statistics. Networks with the same statistic equally likely under the SERGM model. And then we can model things based on statistics generally, and a more general family allows for these weighting factors to be different, and so now we have a general class of random graph models that nest the SERGMs as a special case, but are going to be in a much smaller space and easier to work with and easier to estimate. Okay. And just to emphasize things again, these statistics can encode many things, so these you still have the flexibility that the SERGMs did in terms of links, k-stars, subgraphs, friends in common, etc. You can adapt it for degree distributions. You can do preference-based models. We'll talk about that later. You can allow these things to have node characteristics, so you could be counting number of links between different types of nodes, etc. So this is a very flexible class, and now we've got something down to a manageable size. Okay, so a couple of words before we talk in detail about the nuts and bolts of estimating these things. First of all, we can now ask a question about when will the estimated parameters converge to the true ones. So when is it that when you estimate one of these models, the betas that we end up estimating are going to be close to the true betas with a high probability, right? So nature's generating one of these networks. Now we have to see these things. And then the second part is how do we estimate these things on a computer, right? So one is under theoretical considerations, when is it that if we can compute things, we'll get accurate estimates, and secondly is when can we actually do those computations. Okay, now let me say something which I think is very important in terms of the statistical reasoning of this, and easy to sort of forget. Here we see a single network, and in some sense we're seeing a single data point. So often when we think about statistical estimation, regression analysis, all kinds of other estimation techniques, when we're often dealing with some sort of independence in the data. There's some independence that people take advantage of. And there are situations where there's more dependence, and then people have had to deal with special kinds of techniques to deal with that. So the idea is if you want to estimate, suppose that I'm flipping a coin, and you're trying to figure out what's the probability of heads. So I've got a biased coin, I'm flipping it, and Well, the thing is that each time I flip it, we've got an independent realization of our heads or tails, and laws of large numbers work on that independent sequence. The difficulty is here, we don't get an independent realization of all these links any longer because the links are correlated to each other. The fact that there's triangles mattering and so forth means that we're not getting necessarily just fully independent observations. We're getting one network which was formed from a process which involved a lot of correlation. So we don't have just the independence that allows us to directly pull law of large numbers kinds of arguments into play. But what is true is we still do have many observations of, say, links and triangles. So for counting small subgraphs, we still do have lots of observations. And the idea will be that we can still prove that the estimates we'll get from this will be fairly accurate to the extent that we can show that there's enough information in having lots of these observations to still disentangle what nature must have been doing to generate a network that looked like it did. So they're not independent, but they can still provide enough information to get accurate estimation. Okay. So which of these models might have nice asymptotic properties in the number of nodes for things like maximum likelihood? The exponential form, let me emphasize this, is a wonderful thing to work with. Why is it so wonderful to work with? Well, when we want to ask, so let's suppose that we've got a model, which our model looks like probability of S is proportional to exponent beta times S. And we want to say, what's the beta which maximizes the probability of seeing S? Well, the beta which maximizes that is actually given by this equation. You choose the beta for which the expected value of S is actually equal to the observed data. So the maximum likelihood estimator in an exponential family is you just want to figure out which betas would have given the actual statistics that I observed as the expected value. So for which ones would these be centered at the mean? So the exponential family is a nicely centered distribution in the sense that when you want to maximize the likelihood, it tells you just try and set the parameters so that the actual observation is at the mean, and that's the one that maximizes the likelihood of things. So the maximum likelihood outcome is achieved by finding parameters for which that outcome is the mean of the distribution. So that's a very nice property of this. You can, if you want to read about that in more detail, most statistics books, you can even look on Wikipedia, will give you proofs of this. It's a fairly standard fact of the exponential family, and one of the reasons the exponential family is a useful one to work with. So that gives us a nice maximum likelihood estimation technique. And so then we can prove theorems on this. So let's suppose that we have some sequence of growing random graph models. So we are going to have to talk about large systems. If we just have a few nodes, anything can happen, and so we won't have accurate estimates necessarily. So we will have to have enough observations. So as the system gets large, suppose we've got some statistics we're caring about, some betas which nature is actually using, the weighting factors. So this defines some sequence of SERGMs that we're dealing with. And what we'll have is now, what are conditions under which the maximum likelihood estimator that we had, so this estimate B that's going to come from this, under what situation is that going to be close to the true beta that nature was actually using? Okay, so we'll first say that one of these models is a sequence of SERGMs is expectations identified if there exists some delta such that when you vary the expectation of the, so as if we move to some other beta that's a little bit different from the actual beta that nature might be using. So nature is actually using some true beta n. We're trying to estimate that. And the idea here is, let's suppose that we change things to a slightly different beta. Okay? So let me make sure that we understand the thought experiment here. So nature's really working with beta n. We want to check which betas are going to work, so we're working with some different betas in order to do some estimation. It has to be that as we change the actual betas, in order for us to be able to figure out which beta nature was using, it's got to be that somehow the expectation changes when we change our beta. Otherwise, as we change our beta, we can't figure out that there's any difference in those distributions. We won't be able to figure out which beta matters. So this condition says that there exists some factor where as we vary beta away from beta n, and we look at the expected value under that distribution, then that should be different from beta minus beta n by at least some amount. So if we move the betas by 10%, we should get at least some movement in the expected values. Okay? So this it means that we need some variation in terms of how the model reacts to beta. Second thing is going to have to be true is that we are going to have to be able to get enough information out as the system gets large so that the distribution of statistics isn't all over the place. But if nature's working with a particular beta n, then there has to be a high probability that the actual statistics it's going to generate are fairly close to the mean. Otherwise, since we're working off the mean, if nature's generating statistics all over the place, then we won't know that we're close to the mean. So the concentration is going to say that as the system gets larger and larger, the nature has to be generating statistics which get more and more accurate. So now we've got accurate statistics, plus as we vary beta, the expectation changes. Those two things then allow us to get a consistent estimator. So the maximum likelihood estimator, so this is our maximum likelihood estimator, as a function of the statistic, will actually converge in probability to the truth if you've got these two conditions. Okay? So this is a theorem which now tells us that indeed maximum likelihood estimation can work for SERGMs as long as you've got this expectation identification and concentration. Okay? Now these are general conditions. This is sort of a standard type of theorem that one works with in consistency. So you see these sorts of theorems in a lot of areas of statistics and econometrics. So it's not a novel theorem in terms of its structure, but what it does is just give us conditions that now we can check and see for different models whether these conditions are going to be satisfied, and then whether we can be sure that as we work with enough data, we'll have accurate estimates of the true parameters. So that's the usefulness of this theorem. So consistency, we need appropriate variation from the model. So it has to be that as you change beta, you change actually what the distribution looks like. And then the model has to be large enough so that you're getting fairly narrow statistics around the mean at a reasonable rate in order to be able to distinguish different betas from each other. Those two things will give us consistency. And then we can actually work with specific classes of exponential random graph models in order to get further and make sure that we can check these kinds of conditions. Okay. So that's a lot to swallow. You might want to take a little break now. And then what we're going to do is now we're going to come back and start talking about a special class of SERGMs that we can be sure will estimate nicely and for which we can have simple and fast techniques for doing so. So these are going to be count SERGMs, we'll call. But basically ones that are going to count subgraphs of different shapes. So not counting diameters, but counting things like triangles, cliques of size 4, stars of some shape, links between different types of nodes, triangles that involve 2 females and 1 male. Whatever you think of as different kinds of subgraphs, those are the things that we're going to be counting. And so we'll have a series of counts of different kinds of statistics, and make sure that these are such that we have large numbers of possible things. If there's only we've got a data set with only 2 men in it, then there's not going to be many possible links between men. You're never going to be able to estimate what's the probability of a link between men if there's only 2 of them. So it's going to have to be that the number of possible links between men and your data is growing large as the size of the data set gets large in order to be able to have accurate estimates. So what we'll have to have is, so when we talk about these sequences, we'll have to make sure that the maximum possible count, we'll call this S upper bar n of some statistic j, so we're counting a bunch of different statistics, each one of those has to diverge. And then counting, we can just look at what's the probability, well, the weight that we'll put on different vectors of statistics are going to be based on just keeping track of the different ways in which nature could have arranged those. So if nature picked 100 of the possible triangles out of 1,000 that were there, well, then there's 1,000 choose 100 different ways nature could have done that. And so what we're going to do is just multiply up these probabilities times each other, and that'll be the actual k weight. Okay. Now this is not actually exactly the number of weights that could have had 1,000, 100 triangles and so many links and so many other things, because there can be some interdependencies between those things. But it'll be an approximation of that for a series of models. Okay, so that's what the k's are, is just looking at relative ways in which you could have arranged these things. Now we're going to put in a condition which we'll call not conflicted. So we'll say that a particular SERGM is not conflicted if when you look at some range of possible values that a statistic could take. So statistic j has some expectation, and now let's go epsilon minus about that and to epsilon plus. The product of those things across different statistics is feasible. So an is the set of feasible realizations of the SNs. So this is feasible for all n. Okay, and what would be things that would not be feasible? Well, it's infeasible to have, so let's suppose we have n nodes, it's infeasible to have n isolates and 40 links. Because this means that all the nodes have no links, and this says we have links as well. That's impossible. So what would have to be true is, in order for these not to be conflicted, you'd have to have fewer isolates. So if we only have 10 isolates and we're dealing with 30 nodes, then there's 190 possible links. It is possible to have 40 links. And so what this condition says is, in our range of where we expect the number of isolates to be, and where in the range of where we expect how many links there to be, that we don't end up in conflicts with each other. So we don't end up with so many isolates that there couldn't be that many links, or so many links that we can't deal with the number of isolates we've got. They have to be congruent with each other. Okay, so that's the not conflicted condition. Okay, so theorem, if you're looking at a sequence of these simple count statistics and they're not conflicted, then the maximum likelihood estimator is consistent. It satisfies those earlier set of conditions. And in particular, when you look at if you want to ask how quickly the estimate, so this should be the estimated beta that we're coming up with. The estimated beta compared to the true beta is converging at a rate which is proportional to the square root of the maximum possible value of that statistic. So that, and it's actually normally distributed with a mean 0 and a variance expression, which is based on a binomial calculation. So you've got a fairly simple formula for convergence rate, and you've got consistency. So basically what we need is, if we're doing these kinds of simple counts SERGMs and we don't have conflict, we get accurate estimation, we can do it, compute it. So now we've got some theorems that will allow us to solve a lot of these problems. One last thing, just before stopping for this particular segment, So if we're dealing with these simple count statistics, and I'll talk about another class of ergms in another video that are sufficiently sparse, then an easy way to estimate them will be to actually just look at how many statistics were actually observed. So how many triangles did we observe? How many triangles were possible? So maybe we got 1/10 of the number of possible triangles out there. Then the beta actually corresponds to just looking at the log of the odds ratio. So as if it was just doing binomials on each possible statistic separately. So you can think of nature, so what it says is if you want to figure out how one of these count SERGMs works, then you can actually just look at counting different observations of how many triangles were there, how many links of this type were there, how many links of that type were there, how many cliques were there, and think of nature as just picking those each independently. And by doing those estimations as if they're independent, they're actually going to be asymptotically accurate estimates at a rate which is proportional to the square root of the number of possible observations. So these converge very quickly, in fact. So that's a very useful theorem and a quick way, a very easy way to do estimation in this setting. And what does the sparseness avoid? So let me just sort of give you some intuitions for how this works and what's going on here. Okay, so we've got n nodes. And let's suppose nature's forming some triangles. Well, nature forms one triangle, then it forms a second triangle, and then it forms a link. Right? It forms this link between 1, 3. What we end up with is an extra triangle. Okay? And so what it's saying is, basically nature was randomly picking some triangles, it picked a link, but when we observe this, what we actually count is instead of counting 2 triangles and a link, we actually think there's 3 triangles there, or we can't be quite sure. And so that makes it more difficult to figure out what the actual, how prevalent was it nature in terms of picking triangles or picking links. What sparseness does is it avoids, it means that nature's picking relatively few links compared to the overall number of links. And so it tends not to form too many extra triangles. So if the prevalence of these things is relatively low, which is true in most social networks we look at, right? I mean, I'm not connected to many people out of the world. I have maybe thousands of acquaintances, not billions. And so there's a lot of missing links. And so this means that you don't get too much accidental generation. If nature's picking the triangles and picking the links, you're not going to get too much overlap so that they confound each other. And then that means that the actual estimates, by just looking at each one of these independently, turns out to be an accurate estimate overall. And so that's the idea of the theorem. So these kinds of things that are sparse enough, and many observed networks are sparse, then you can estimate these parameters directly using proportional techniques. And now we've got an estimation technique which is extremely quick, extremely accurate, direct, and it'll give us those betas directly. So when they're sparse enough, we basically are avoiding a lot of the problems that we have with tensor graphs. Okay, so that was a quick look at SERGMs. There's a lot more to be said on this subject, but that gives you an idea of some of the issues that are out there in terms of working with these models. And we'll also talk about other variations on this and fitting these things in more detail. And then the next major topic that we have is all of these models we've been looking at so far, the static models, the growing random network models, these variations on exponential random graph models. These are all models of random network formation. The nodes aren't picking things. Nature is just randomly laying down links and so forth. And we can also imagine in a lot of settings we actually that there's some structure to why certain links form and other ones don't. Strategic trade alliances are not arising completely at random. Countries are very carefully choosing these, and we might allow the people to choose them, even who I collaborate with or who my friends are. Those are choices I make over time. And some people I get along with, some people I don't. Some people are very easy to get along with and so forth. So there's going to be a whole series of things that matter, and we can think about voluntary choice of networks and try and understand what that is. So that'll be our next major topic.